I think we're ready for the last lecture today, and also I think the last lecture in the biology section of this year. This lecture is by Constantin Teleman, who's a professor at the University of California in Berkeley. He obtained his PhD in 1994. Has received many grants and prizes, including the Whitehead Prize and the Senior Berwick Prize from the London Mathematical Society. Constantin will talk about gauge theory and mirror symmetry.
Thank you for the introduction, and thanks to the committee for the invitation and organizers for running this very nice show. I've actually given several versions of this talk over the past 2 years without ever getting it right, but I'm not a quitter, so this is yet another attempt. But I will keep this one, especially since it's a topology audience, not a mathematical physics audience. I'll keep the speculation to a minimum, and I'll try to make it clear what it is we know for sure and what is left to work out. Now, what the talk is really about is categorified representation theory of a compact Lie group, especially the connected Lie group situation, not the finite group, which is the model somewhere. And what I'll try to convince you about is that there is a good theory of such things, there is a good character theory of such things, it involves geometry, and one can compute real answers to real questions from it. I won't have time to actually do a computation, but having done one, actually there is one in the paper, having done one, there's a high degree of confidence that the story I'm telling you is correct. So which way do I point this? Do I point at somebody? Hey, it works. Right, so this is a character theory for a group, the group being SO3 acting on categories. I have to explain to you what that means. So what are we looking at? Well, let's ignore the right picture for a moment. Yes, so while I was preparing the slides, my computer gave up the ghost. I hope it wasn't a comment on the quality of the mathematics, but I had to finish the slides on the iPad, so there are some limitations. But it is possible to type presentation on an iPad. No. Anyway, so let's ignore the right half of the picture. On the left half, we're seeing a space in the center of many colorful things with two projections. A projection to the base is conjugacy classes in the Langlands dual group of SO3, which is also known as SU2, and you see the plus and minus, the identity in there. I've written that space as a maximal torus model of the Weil group. On the left is a projection to the Lie algebra of, it's actually of SO3 in this case, no, it matters, model Weil group again, and 0 is a distinguished point. And the space itself maps almost 2 to 1 to the product, so it's not the product of the two. And what the space is, very precisely, is if you take the product of the torus and the Lie algebra, so the cotangent bundle, if you like, of the torus T check, and divide by total Weil group action by Z mod 2. Then you get a manifold of two singularities, rational double points at plus and minus 1 and 0. Then you blow them up, you get a smooth space, and at the very end you remove the squiggly line, which is the proper transform of the zero section of the cotangent bundle. And that's a space you get. It's also known as the Hitchin manifold. In the literature, it's a holomorphic symplectic manifold of some interest. So I've drawn some curves in there. There are two lines that the cotangent fibers over plus and minus 1, and those are two distinguished representations. They're categorical representations of SO3, but what they are representations of pi 1 of SO3, honest representations, a trivial one-less sign representation of Z mod 2. And they sit over plus and minus the identity in the Langlands dual torus. Remember, the center of the group is, of a simple group, is do, the set of characters, one-dimensional characters of pi 1 of the do. Then there are the exceptional divisors in dark green, and they play the role of the regular representation of SO3. And finally, there's a squiggly line, which is a general representation of categorical representation of SO3. And in 2 dimensions, you can't say anything about it. In general, we have to be a Lagrangian in the holomorphic symplectic manifold. And it meets a distinguished representation. So it meets a trivial representation. Well, what's home between the trivial representation and the representation? If there's any sanity, it should be the invariant part of the representation. That's what it is. And what's home between the regular representation and the representation? Well, that's the underlying space or object of the representation. So indeed, the intercept of the green lines are represent the underlying category. So that's what character calculus looks like in this world. It's going to be a calculus of holomorphic Lagrangians and the holomorphic symplectic manifold. In fact, if you really want characters, they would have to be coherent sheaves supporting those Lagrangians, rather than, say, functions on conjugacy classes. And the underlying space is a double of the conjugacy classes. You can think of it, and it won't be too wrong, as the cotangent bundle of the space of conjugacy classes. Now let's look at the right picture, and there I've drawn some curvy things. Those come from a Lagrangian foliation, holomorphic Lagrangian foliation of the space, and they correspond to some interesting, what might be called irreducible representations of the group SO3. They come from the Fukaya categories of E1, with the obvious action of SO3. And this picture generalizes to any semi-simple. So this is the end of my talk. Now let's start from the beginning. Alright, so the beginning is about Gromov-Witten theory, just because essentially all examples I know, all interesting examples I know of categorical representations come from there. And Gromov-Witten theory is one of the topological field theories that's still enjoying interest after 20-something years in its discovery. It's almost unheard of in physics-inspired math. So I'm assuming, I apologize if this is far too basic, but just to remind ourselves, if you have a compact symplectic manifold, you want to associate to that a 2-dimensional field theory. Space plus time have 2 dimensions. The space, let's think of it as a circle. So to the circle, there has to be associated a Hilbert space of states. That turns out to be the cohomology of the manifold. Now, if you have a space-time, which is a surface with some time slices, some boundary circles, then you specify a state for each boundary circle, so vector in the cohomology, and you're supposed to get a number from it. That's what the field theory gives you. And that number counts the number of pseudo-holomorphic maps to X with incidence conditions specified by the cohomology classes or the Poincaré duals. And it's all topological, so we can assume the circles really are points in the surface. There's no information lost. And this gets more interesting when you remember that, well, you can vary the complex structure on the curve. So if you do this for the universal surface, instead of numbers, you get cohomology classes on the Riemann-Wurth spaces. And still to this day, we don't have what could be called a structural classification of such invariants, meaning we don't know how to write all the invariants in terms of some basic ones. We know there's a lot of redundancy in these numbers. But the most promising approach involves mirror symmetry, proposed by physicists about 24 years ago, I think, refined by many others. And it promised to reduce Gromov-Witten theory to, instead of computations of holomorphic map to holomorphic map, which is rather difficult, to more standard computations on coherent sheaves in the complex geometry of a conjectural complex mirror manifold exchange. And this was fairly quickly developed by Kontsevich with the goal of explaining it, and also the goal to spell out the structure of the invariants one gets out of it. And the key idea was to extend the field theory, the structure I described before, to include surfaces with corners. And the corner, well, 2 edges at the corner, you have to think of them in 2 different ways. One is space, one is that which ends suddenly, and the other is time. So at the place where space ends, you know from physics, you should specify a boundary condition that tells you whether you walk to the end of the world and you see yourself in a mirror, or if there's some radiation coming in, or whatever. And that boundary condition, of course, propagates in time. So one of the edges meeting at that point carries the boundary condition. In topological theory, you actually don't propagate in time. The boundary condition will have to be constant on that, whatever edge it's sitting on. So, turns out, after giving a cartoon argument, it turns out the boundary conditions form a linear category with some structure. That reminds me of a comment of Ed Witten's, who said that when mathematicians define some new notions and don't want to commit to doing anything in particular with them, they say that they form a category. So, boundary conditions form a category. But the category has some structure, and that has been spelled out. So one name for it is a Calabi-Yau structure, or technical name is a cyclic A-infinity structure. And if you add something I'll not talk about at all, it is believed, and there's a theorem now, that having enough structure on the category, you can determine all the Gromov-Witten invariants, all the invariants going with closed surfaces. Actually, I don't think I know an example where one computed Gromov-Witten invariants in this way, but in principle it's possible. So Kontsevich also identified the categories that should form a mirror pair. On the symplectic side, this should be Foucault's infinity category associated with symplectic manifold. I won't say what it is, except it's built from Lagrangians, and so objects are Lagrangians, and Hom space are based on the intersections and the count of pseudo-holomorphic disks. So they involve all the right ingredients. Lagrangians are good boundary conditions for pseudo-holomorphic curves. Pseudo-holomorphic disks should come in because, after all, you want to say something about pseudo-holomorphic curves. So that's all the right ingredient. On the complex side, the category is actually let's say, derived category of the coherent sheaves on the mirror, but it's really you want the A-infinity structure on it, so it's really the differential grade category. And there are many examples now where the categories on the two sides have been matched. I think Zeidel's calculation for K3 wasn't with the early ones, but the Del-Fezzo surfaces were done. The Toric Fanos by a large collaboration, including Mohammed Abu Zaid. And I think the most recent result I know, but surely not the most recent one, not completely up to date, was Sheridan's verification for Calabi-Yau hypersurfaces in projective space. The one I'd like to say more about is the case of a toric variety. Namely, the mirror of a toric variety with a torus T, let's say a complex torus TC acting, is as a space the dual torus, but that would be non-compact, so not very good. It's compactified in a sense by the addition of a superpotential, which is typically a Laurent polynomial. And what goes with that is not. There's no pointer in here, is there? Huh? There is. What goes with that is not a derived category of coherent sheaves, but a deformation of it given by a superpotential. It's called the category of matrix factorizations. And all I want to say about this is that first, you're forced to give up the Z grading, and remember Z2 grading only. And maybe one useful thing to say about it is, see, the space associated to the circle in this setting is going to be the Jacobian ring of a superpotential. So that's one simple thing you can say about it. That's the space which is meant to give you the cohomology of a toric variety. The quantum cohomology. All right, let's see how this mirror arises, because that's what I want to get at. So, in fact, the first examples of Gromov-Witten invariants were computed completely, where for varieties that were described as quotients, Hamiltonian quotients, or GIT quotients of simple varieties. And toric varieties, for example, are quotients of a vector space by linear torus action, and you can describe the mirror completely from that construction. And this construction is due to Giventhal and some independently by Hori and Vafa. Hori and Vafa, indeed, they use this motivation from physics to think of it as a Cn gauged by some torus. I don't actually know what Giventhal's motivation was, but it must have been related to this. So let's start with an example, which the best known example is Pn minus 1 the way. So it's Cn quotiented by U1 acting diagonally. And the mirror in that case, the torus of rank n minus 1 with superpotential, the sum of the coordinate functions, provided you write C star n minus 1 as the set of z's in Cn, actually Z star n, whose product is equal to Q. And Q is a parameter which you can choose freely, and it's the exponentiated symplectic form, basically. You have a parameter in the symplectic form you can scale. So it's right, at least parameter count is correct. So for example, the Jacobian ring of this is meant to be isomorphic the quantum cohomology of Pn minus 1. It is. And the general procedure, if you start with Cn, the standard action of C star to the n on it, you declare the mirror of that to be C star to the n again, but not the same C star to the n, the dual C star to the n, the dual torus. And declare that the superpotential you should write, is just the sum of the coordinate functions before. And now, if you realize the toric variety as a quotient of Cn by some subtorus, C star to the n, then dually as a surjection from C star to the n, the dual torus. And the mirror then is a fiber of this surjection over a point Q. And Q is again a symplectic parameter. In Gromov-Witten theory, it will track degrees of holomorphic curves. It will tell you how to do the Hamiltonian reduction. You need a parameter to do the Hamiltonian reduction. So it lives, if you like, in the exponentiated cohomology of Y. So that's a construction we did before. This is general. And experts will probably know this is not quite right if X is not final, but I'm not an expert, so it's good enough for me. All right. So actually, this is a rather simple construction of something very complicated, so maybe it's worth understanding. So let's see if we can understand mirror symmetry for Hamiltonian Lie group quotients, Hamiltonian quotients of a compact Lie group action. And here are the basic questions, I would say. First, given a Hamiltonian group action on X, what does that correspond to on the mirror manifold X check? And if you've never thought about it, you'll be surprised to hear it's not a group action. Not at all. The mirror of a group action is not a group action. Second, of course, having figured out how to describe on X check the datum corresponding to a group action, figure out how to describe the mirror to the quotient of X. Right. I think we can agree it's a basic question if you want to describe mirror symmetry in conjunction with Hamiltonian quotient. And based on the previous slide, let's see what was on the previous slide, where you were taking a mirror, mapping it to something and taking a fiber to the dual of a torus which was acting and picking a fiber. Based on that, there's an obvious guess in the torus case. And the obvious guess is actually correct for zero torus. First, the mirror to an action is a holomorphic map from the mirror of the dual torus. And second, which I would say is conjectural, but it's within range of being proved. I think it's provable, let's say, I think, with existing technology, I think, is that the mirror of the GIT quotient is the fiber of X check over 1. Derived is not heteroscalary, but it means X check the fiber might be singular, so you have to be careful when you compute the fiber as well. So, I mean, that certainly would be consistent with what I said a second ago. So, if X check was C to the n and T was a subtorus K of C star to the n, that was the procedure of the previous paper. And we can continue to be bold and generalize to any group. That turns out not to be as dumb as it sounds, actually. It's going to be a good minus first order approximation. It's not a zeroth order approximation. It's a singularity, so to say. The mirror of a G action on X is a holomorphic map from X check to the space of conjugacy classes in the dual group. Certainly that generalizes the torus case. And the mirror of X mod G, well, I could have said that it is a fiber over 1, but that would be wrong. So let me just say, with things that will come up later, it's related to the fiber. So conjecture 2, I have to say, I don't know at all how to prove it. There's a map from one to the other, so to speak. And there are baby analogs of it. For example, if you use deformation quantization instead of the Fukaya category, then it becomes an easy statement. But I don't know how to use that to approach a proof. So what I'll do instead, I'll explain why this is something computable and what one can do with it. An example that actually works beautifully. So, to see a little bit where this could come from, let's go back to my childhood. Actually, it was well before my time, but I did grow up learning this. So, when I grew up, I had a symplectic manifold and you wanted to quantize it, you were getting something completely different. You're getting a one-dimensional field theory, also known as quantum mechanics. In quantum mechanics, you just have a space. And how do you produce a space, a graded space in this case, from a symplectic manifold? Well, first, you have to assume you build a line bundle on X with curvature omega, and second, you need to polarize it with a complex structure, for example. And then its Dolbeault cohomology would be the space of states. So that was the quantization of a symplectic manifold. Now, Hamiltonian G action on X, if you're lucky, will quantize to an action on the space of states. That's a quantized action, if it preserves a polarization. Now, there is something called the classical gauge theory, which is what we model by the symmetry. And the space going with that is a symplectic quotient of X by G. On the other hand, there is you can gauge a quantum theory with the symmetry and just means taking the invariants in the space. You could argue whether invariants or co-invariants, but it doesn't matter much for a compact group space. So at this point, you already have a puzzle because there are two ways to quotient. One in the classical world, one in the quantum world. So you could presumably mean two different things by gauging the quantum theory. But the famous theorem of Gilliam and Sternberg tells you that, in fact, you get the same answer. That if you take the classical quantization, where is it here, and take the classical quotient and quantize that, the space you get is isomorphic to the invariance in the original quantum space. And this is helpful in studying symplectic quotient, the topology, and especially the K theory, largely because we understand the representation theory of a compact group very well, so we understand the quantization, this part, very well. We have an effective way to compute it. So clearly, if you want to replicate that for Foucault categories, you need to understand the representation theory on categories. All right. So let's talk a little bit about group actions on categories, and I'll give a basic definition and become more sophisticated later. So what's an action of a group on a category C? At this point, you can think G is discrete if you want it. So first you want that should have been an autofunctor of C, of the category, for each group element. And then the functor is an automorphism. And, little bug, okay. A natural isomorphism from the functor associated to the product to the composition of the two functors for each pair of elements G and H in the group. And there's of course a condition. So you see, before, when acting on a space, you were just putting an equality here, saying that the operator of the product is the product of the operators, but with functors that doesn't make sense. You have to put some data, an isomorphism. And once you've done that, there is a possibility of having coherence problems later, and you do. If you have a triple of elements, there will be in fact two ways you can get from phi of GHK to the product of the three, and the coherence condition is that the two ways to do so agree. And that turns out to be true. And the first comment is that it's for people who like this language. This is a homomorphism from the group G promoted to a two group in the trivial way, the two group of autofunctors of C. That's what it's being described. Yeah. Now, I said topological group actions, and I mean several things by that. First, G is a topological group. You probably want to say that C, the category, is a topology and the action is continuous, otherwise it makes sense. And there's a third condition, that's the important one. And this condition will say that G really acts only by means of its topology. Or if G was contractible, the action would be equivalent to a trivial, indistinguishable. And that's one way of formulating the condition. And you can see then how the topology of G will prevent even trivializing the action. You you trivialize the action in the neighborhood of the identity, then you can try to extend the trivialization on the whole group, and of course when different paths they meet, you can have a discrepancy. So at least you can see that pi 1 is going to come in, which isn't quite good enough. You'd like the whole topology of the group to come in, and that will happen in the derived version if you relax the coherence maps to coherent homotopies. So I'm not going to make precise a topological up to coherent homotopies action of G on a category, because the ways I know to make it precise almost certainly don't work for the interesting examples. So instead, I'm going to get to a conclusion which can be made precise and is almost certainly true. Okay. So instead of telling you something precise with no examples, I'll tell you a little later something that looks more specialized, but which is almost certainly correct in a large class of examples. All right, and the other ingredient we'll need is how to compute the invariance, and I'll just give a definition in the discrete case if you like. So what is the invariant category? Well, it has objects consisting of tuples, so one object of X, together with a collection of isomorphisms between the object and its transforms under the functor. And there's obviously a coherence condition there, which I will let you think about if you want. And morphism would be just morphism from X to Y, which commute with this additional structure. So that's how you define the invariant category. And if you've never done the exercise, if the category is out of vector spaces and the action of G is defined to be trivial, so all the phi G's are the identity, what you discover is a category of representations of G over vector spaces. The fixed point category can be bigger, so to speak. It doesn't have to be small. All right, so now we're talking about topological action of the homotopy, and let me tell you a topologist way of describing that. So here's an actual theorem. And if you make precise definition on the previous page, where was it? Somewhere. You have derived version relaxing these conditions to coherent homotopies. If you make that precise, one of the formulation to arrive at, when G is connected, is that you'll only see the topology of the based loop group appear. It will act on the Hochschild cohomology of the category. That's a derived version of the center. Because omega G is a double loop space. It's a double loop space of BG. The chains on that have an E2 structure multiplication, first order of commutativity. It's a classical theorem now, known as Durin conjecture, that Hochschild cochains on a category have an E2 structure. And an important part of this statement is that this isomorphism is compatible with the E2 structure, so first order of commutativity. That will contain the information of a topological action of G on a category. If you don't like E2, but you like tensor categories, you could say that this is the module structure of the category acted upon over the tensor category of modules over chains on omega G. Because the E2 structure here will give you a tensor structure on the category of modules over this scale. So you can tensor the two of such things over chains on omega G and still get a module structure for chains on omega G. So it's a matter of taste which one you choose, but this is the same thing. So you make C into a module over this tensor category built from the group, or you get a map of Hochschild cohomology. This is more concrete actually, even if E2 sounds disturbing. You can actually compute things with using. And this being said, the invariant category is the fiber of C over the point 0 in the base point in this ring. And you see, since I mapped this ring into the center of the category, it means I can sheetify C over spec. And the distinguished base point, and the fiber over there is base. And here's the theorem. If you have a Hamiltonian G action on a compact manifold, deflecting manifold, you do derive a topological G action on the Foucault. So the benefit of this definition here, or theorem, take this as a definition, is that you get it right away. Any proof you want to write of this theorem will be objected to by someone. But that's true of any proof you write about any statement of Foucault categories, I think. So, but let me tell you quickly why this is true. Well, what's the problem? The problem is there's no functorial construction of a category just from a symplectic manifold. you have to put the holomorphic structures, and then when you compute home space, you have to start perturbing to get transversality. And there's a gigantic amount of work involved in proving the following theorem, or almost theorem, depending who you ask, that the space of all these choices is contractible. So from the point of view of homotopy theory, it's as good as having no choice at all. So any homotopy theory conclusion will carry through as if there was a functorial category you could build from a symplectic manifold and not no other choice. If you try to say more, it becomes a bit more question. At least that's my story, and then sticking to it. All right, so there's some history to this. If you drop E2 in the statement, this goes back to work of Paul Seidels. I think he may only have stated something about pi 1 of the Hamiltonian symplectomorphism group, which of course which is pi 0 of this, so just a reduced part. Now in our case, the homology of omega g is a fully commutative algebra. I'll remind you in a second what it is, over C. And we expect the same to be true of the Cauchy cohomology of the Fukaya category, at least when some nice things happen. It's meant to be the quantum cohomology of the map. So we have up there a homomorphism, at least if you pass the homology, of commutative algebras, the source of which is even a free polynomial algebra usually, which is symmetry. So it might seem that there's not much to say in this story about E2 and tensor categories, but that's not true. Saying that the map is an E2 map actually contains one thing. So you need that E2. All right. So what does this give us? Well, it gives us the spectral decomposition of a G category over spectrum. And when G is a torus, well, all there is in omega G is pi 1 of the torus, and then you get the group ring of pi 1, and that's a ring of functions on the dual torus, exactly. So that spectrum is exactly a dual torus. It's very good news for our naive conjecture that the dual torus would be. When G is simple, that space is a vector space, a gradient vector space. So the analog of quantization computes with reduction, which I would say is a main conjecture in this story, is that the fixed point category for the G action is the Fukaya category of the GIT quotient. That's a main conjecture. So if you follow what I just said, you expect that you can compute the Fukaya category by shivifying it over this vector space and computing the final over Z. 0, of course, would have to be called 1 in the case of the dual torus, and if you, in the case of a torus, it's exactly naive conjecture we had a few pages back. You compute the mirror the GIT quotient by taking the fiber over 1. You have a map, the dual torus, the fiber. So that's great news. Maybe we don't remember the conjecture. Sorry, I don't know how fast. Rewind. Oh. Right. So we wanted to map the dual torus and the fiber over 1 for the GIT quotient. But for a non-abelian case, we wanted a map to conjugacy classes. And the spec of the homology of omega G is not very much like the space of conjugacy classes on the dual group. So that would make the original naive conjecture wrong. And nobody likes to be wrong. So the story doesn't end here. In fact, if you start doing calculations, you find this version of the conjecture is wrong. Very often compute 0 when you should find faults. So there's something wrong with that. And if there are homotopy theorists in the audience, they'll probably guess where something went wrong. The homotopization of the notion of the G action is too weak. And here's an analog topologist note. If you go back to representations of a group, you can weaken the notion of a representation to a homotopy coherent homotopy representation. And then when you try to compute the representation ring or the K group of that category, instead of getting the representation ring of G, you get the K theory of BG, which is a completion of this. So with complex coefficients, this is the ring of characters on the functions of conjugacy class or characters. Whereas this guy is completion at the identity. So making things to be too loose leads to a completion of the rings you're computing. And what happens in some examples here, you're completing in the wrong place, you can't calculate anymore. Just like here, if you're trying to discover the value of a character at a point away from the identity, just with this information, you have to. So that's what's wrong. So what is needed is something a bit stricter than the homotopy G action. So basically, whenever G, the group G act, that has to be strict, and everything else has to be up to G homotopy. So in particular, one part of structures need to map between these things. Well, G acts by conjugation on both sides, and you want it, whatever you've done to produce this map, you want to strictly commute the G actions. Sorry for the technical aside, but it explains something important. It's kind of what I think what has held up progress in this for some time. But let's interpret that in terms of something more concrete. So before I talked about the functors phi g which define the action of the category, let's look at the homomorphism from the identity from 1 to phi g for varying g. You get a complex of sheaves on G if you look at derived homomorphism of functors. And this complex is multiplicative essentially because the functors composed according to the multiplication of G is going to be lifting, if you like, of a multiplication of G to the stalks of these sheaves. But we had said, remember, that a topological action requires these functors to be identified with the identity in a neighborhood of 1 in G. So in fact, this complex of sheaves is a local system. Before, we had the homomorphism from omega G, a topological one, to the fiber over the identity. Well, what could that be? Well, it's a holonomy action of the local system of G. That's where that comes from. So maybe a soft picture is that if you remember just the units, the invertibles, the isomorphism from the identified G inside these sheaves, what you get is like a central extension of them by the units in the. Now, this system is invariant the conjugation essentially because of multiplicativity, and we're going to insist that it's strictly equivalent. And what this does is it enhances the previous structure of on Hochschild cohomology, the structure of a modular over the base loop group to an equivariant structure. Now, let's relate that to some desirable things, some things we want to know about. So optimistically, when X is compact, the Hochschild cohomology of the category is a quantum cohomology. So over G, you get a multiplicative and equivariant local system with fiber, the quantum cohomology of X. You can form its equivariant equivariant cohomology, so cohomology of G with coefficient of this local system, and equivariant for G, and this has a product by multiplication. And quantization commutes with reduction conjecture for categories implies that what you compute here is isomorphic to the quantum cohomology of the quotient. So you can compute that. If you take X to be a point, that's not so good, but you can twist the story, you can twist Gromov-Witten theory, and what you get is a gauge theory in 2 dimensions known as topological Young-Mills. If you also replace letter H or letter K, you're getting a twisted version of G equivariant K theory of the group G with multiplication. And by a slightly non-trivial theorem, that is isomorphic to something like Lindemann in conformal field theory. So this generalizes those results. So it's like a Young-Mills theory with coefficients. This is what the Gromov-Witten theory of a quotient. There's more structure which can be seen from here. If you include 1 in G, you get an algebra homomorphism from the Giventhals equivariant quantum cohomology to this total equivariant cohomology. And this map has already been defined, honestly, in terms of pseudo-holomorphic disks named in this structure by Woodward. It's known the quantum kernel. So this. If you do have, if you manage to get this picture through, a lot of the structure known equivariant Gromov-Witten theory is spelled out very clearly. I mean, it becomes obvious once you have built the objects. Okay, so now let me tell you the correct versions of the conjectures and some of the theorems about the character theory of categories. They're theorems if you ask for G to act on a category, and they may be conjectural or partly conjectural about the Fukaya categories, compatibility manifold. So the space we're going to look at, so as I told you earlier, the Hochschild cohomology of the category used to carry a map from the homology of omega G, and now this has been made equivariant for the group. So the space we're looking at now is spec of the equivariant homology of the base looping. And thankfully this has been studied by some very capable people, and they've proved some beautiful theorems about this space. It's an algebraic symplectic manifold, and it has a nice realization as a holomorphic symplectic quotient of the cotangent bundle of the group, provided you tweak it a bit. A more complete presentation is you start with the cotangent bundle of the torus and divide by the Weyl group, resolve singularities, and throw away some proper transforms of divisors, which can be spelled out. This space projects, if you remember the projection, the cotangent fiber to the algebra. There's the well-defined projection of the quotient to coadjoint orbits, and the fiber over 0 is in fact the earlier space we're trying to play with, spec of the homology of the loop group, and it's a Lagrangian submanifold inside. So the first attempt at spectral decomposition was only seeing this Lagrangian inside a submanifold. Finally, if you complete the space, that neighborhood, you get something called the two-Hochschild cohomology of the Lagrangian, and that's also known as a cotangent bundle. And just to tell you where this relates to anything, this E to HH star controls formal C2 automorphism and deformations of an algebra. An E2 action of the homology of omega G micro-localize the category to the neighborhood of the Lagrangian. And the strict G action macro-localizes it to this ambient symplectic manifold. It's an undoing of a completion which is done by formal deformation. So it's the clever uncompletion of the sort of homotopy softening of the action, and it turns out to be correct. Let me draw it again for you. So we see here the cotangent bundle of the dual. So that's the group was SO3, so the dual group is SU2. It's a cotangent bundle divided by the torus divided by the Weyl group, blown up. There are two exceptional fibers, and with a zero section removed. So it ends up being F. And these exceptional divisors, these two together are spec of chain of homology of omega. Something happened to G here. It was supposed to be a G. And the vertical fiber over 1 used to be, is the trivial representation of the character. And finally, what's the foliation on the right? Well, let's explain that. Now, in this picture of categorical representation, Schur's lemma is going to fail. So, you see, if it's true that the characters live on Lagrangians, you see, you can have two irreducible Lagrangians intersect, and you see them here, without agreeing. So, you can have home between irreducibles, which are not isomorphic. There's not going to be such a thing as a unique decomposition into irreducibles. But you can ask, are there some distinguished irreducibles that allow us to study the entire space? And the answer is yes, there's a distinguished holomorphic Lagrangian foliation of this space. And seems to serve in practice the spectral decomposition for categorical representation, and the geometric setting, coming from Fukaya categories, this is related to the foliation by coadjoint orbits under the moment map. So that's where it comes from. It comes from yet another construction of the space, the holomorphic symplectic quotient. We divide this time by the groups of upper triangular matrices, but you have to reduce not at 0, but the regular important character. And the cotangent fibers on the right correspond to the Fukaya categories of G flag varieties, of G check, yes. And this is actually a theorem because those have already been, the mirrors of flag varieties have already been computed by several people, some of them are in the audience here, but probably the most comprehensive description is due to Constantin Teleman. And the story I told you, I don't have the time to explain, obviously, But the story I told you does allow you to compute the mirrors of flag variety and you do recover exactly which is construction. And I think my time is up.
Yes, sir?
So instead of using, so you stated the theorem is involved D2 algebras, but instead of using the little disk operand, one could imagine that the framed little disk operand would have played a role in the theorem, because both, if I replace the tagonalies by cocktail cohomology, that's a framed little disk algebra, and so is the double loop space of G. So, but they're both kind of trivial.
You mean you want to put the circle action and make that circle
Or keep
equivariant?
track of it, because
Yes, I don't know. Yes, I'm not disagreeing. Yes, but I don't know how to use that.
yeah,
That's
and also your theorem is correct as stated.
yes, yeah, no,
And
but
so
it allows you to compute
replacing
things.
E2 by the frame one would change the theorem, but I wonder what it would change it to.
Well, see, one problem when you put the circle action in is you use the product. That contracting product relies on not having an S1 action. Just a pair of pants doesn't carry a circle action. So you gain some structure on some sides but lose some. So yes, but probably you're right. That structure appears but has been studied in string topology, which is a special case of Gromov-Witten theory. So probably there is an equivalent structure here. I don't know if it's been studied for compact manifolds to give something. Good point. Yeah.
I think we have time for another question.
So the way you described the mirror construction in the non-abelian case earlier seemed to be, for example, for something like Grassmannian, seemed to be related to this abelianization business. On the other hand, Constance's construction involves, as far as I understand, Lagrange duality, but for GLN and not GLK if you take Grassmannian Kn. And seems to be more related to this like toric generation of the Grassmannian rather than abelianization. And so I mean, for me, it's not clear to actually how to relate the two directly, other than you calculate things on both sides and you check that.
She has more constructions of mirrors, I think. And the one I'm referring to is the one where she doesn't say GLN, just writes G and G check, and that's the one which I've checked. It is exactly what
so
you get
that
from
is
me.
really.
But I mean, for the Grassmannian, I think there's probably more than one construction. And then
My understanding is that the one in the paper with Marsh, I believe, where she talks about Lagrange dual is about actually Lagrange duality for GLN. So I thought maybe you have some.
No. There's a
insight
paper.
as to-
I think it's in Advances where she writes it for all G and all flag varieties, and what she gets is exactly what we compute from here.
I can ask later.
All right.
Last question.
Let me ask you one question and one comment. The question is your definition of an action of category reminds me very much the work of Bob Thomason about Lux functors from the beginning of 80s. Well, he was working in discrete categories, but probably one can expand his definition to enrich categories. So is it?
Yeah, I made no claim to originality on that one. I just didn't know what attribution to write. I mean, it's sort of, but it's quite possible. Yes.
He defines many
Yeah.
notions like homological limits for several functors and so on, and probably also homological limit. And the other point is you said that you cannot recover a representation ring out of homological information, but just a completed representation ring.
Right.
This is not quite the case, because if you take the monoid of maps from BG to BUN, and then you complete it to the group, then you get actual representation ring without.
Yes.
completing.
So I don't want to go back on the slide, but I did put a parenthesis the word stable, which means I'm not allowing exactly what you're saying. You let n go to infinity first, then you map, and then you can't get it. Otherwise, you're correct. If you fix the rank, if you don't stabilize, for connected groups, I think you are correct. You can recover it. But there is a parenthetical stable in there, and that's exactly what it means. I was afraid that the topology audience, somebody would catch me on that one. That's why I put it there. Thank you for noticing it.
Well, let's thank Constantin again.